So yesterday we started 9-6, which is graphs of polar equations. Yesterday we talked about, well, we graphed a circle. We're going to get more in depth on those today. We graphed a circle. We talked about symmetry. We graphed a limison, and then we talked about roses. So a quick review of some of the stuff we talked about yesterday. This was your general test for symmetry. So without shortcuts, we use these things. If it's symmetric to the pi over 2 line, then you would change both the r and the theta, and it goes back to the original. If it's polar axis, you would change the theta. Again, it would go back to the original, so this is like a cosine situation. And then if it's symmetric to the pole, you would change the r, and it would go back to the original. So today we're going to see something with r squared, and that would be like the pole. What I do want to add about symmetry, these tests for symmetry, is that just because it doesn't, so if it has, we're using our shortcuts, right, which are sine would be symmetric to the pi over 2 line and cosine would be symmetric to the polar axis. It doesn't mean that if it has sine, it does not have symmetry to the polar axis. It can have those other things. It's just not guaranteed. So when we talked about yesterday, we talked about a rose, right? So if I have a rose that has 4 petals, this actually has symmetry to all 3. So this is either going to be your sine or cosine. It's not going to be both. You're not going to see both, but it does have symmetry to all 3. So it's not like we're using these to rule things out. You're only using the shortcuts to say what it is, okay? But again, if it doesn't have sine, if it has cosine, it can also be symmetric to the pi over 2 line. And if it has cosine and not sine, it can be also symmetric, or sorry, the other way around. It can also be symmetric to the pole. And then if it has sine and not cosine, it can also be symmetric to the polar axis. So it's not that they can't happen, it's just that it's not guaranteed. Yeah.
So if it's like that, then it's symmetric to...
This is actually all 3. This would be to the pi over 2 line because I can fold it along the y-axis and it overlaps. To the polar axis, I can fold it top to bottom, it overlaps. And diagonally, what happens in the first quadrant happens in the third quadrant, what happens in the second quadrant happens in. So this has all 3, but this is a sine curve equation. Does that make sense?
So how would you know that?
So you're not using them to rule them out. You're not saying it has this and doesn't have this. You're saying it has this for sure. It may still also have this. So you're only using it to help you know what it does have, not necessarily what it doesn't. Does that make sense? Yeah. So when you looked at the ones we did yesterday, if I look at something that has cosine, I'm saying it's symmetric to the polar axis. I'm not saying it can't be symmetric to the pi over 2 as well. With a limison, it's going to be different. A limison's one or the other. But with a rose or a Lemnis Gate, you could have both. Actually, not a Lemnis Gate. A Lemnis Gate, you could also have both.
So how do you know,
So you're only using it to say what it has, not what it doesn't have. You can't.
How do you know if it's a rose?
Oh, that's based on the equation. So, right, so yesterday we talked about the limisons are your plus and minuses, right? If I have something and I'm adding or subtracting something to that trig function, then it's a limison. We talked about this slide. So again, I would make sure that especially if you're a visual person, keep this slide in your mind. If you look at this first one, which starts with an inner loop, and I know that that is my smallest a over b, so it's less than 1. And then you picture something physically pushing that loop out. The next thing it would be is that heart. The next thing it would be is the dimple, and the next thing it would be is flat. So if you could push something from the right to the left, pushing that inner loop out, it goes in that order. So it's smaller than 1, equal to 1, in between 1 and 2, and then greater than or equal to 2. So inner loop to cardioid, which is the heart, to dimpled, which was that kidney bean, to convex is that last one. Then we talked about the rose curve. So I know it's a rose if it has a number attached to the theta, but r is still raised to the first power. So today we're going to get into Lemnis Gates, and that's when r is squared. Those also have a number attached to theta. So it's important to differentiate them. A rose has r to the first, but a number attached to the theta. If the number attached to the theta is odd, then it has that number of petals. If the number attached to the theta is even, we double it to get the number of petals. Now we're at circles and Lemnis Gates. So yesterday, the very first one we graphed is a circle. If you are not adding or subtracting anything to your sine or cosine, if you don't multiply the theta by a number and r is raised to the first power, that is a circle. So it can be r equals 5 cosine theta, r equals 5 sine theta. And I would know the symmetry based on the trig function. If it's cosine, then it's symmetric to the polar axis. So it's either going to be on the right or the left if it was a negative on the front. If it's sine, then it's going to be symmetric to the pi over 2 line. So it's going to be above or below, again, depending on the sign on the front. That value on the front is your diameter. So that's the furthest, the biggest R you're going to get. When you plug values in, that's the biggest R you're going to get. So having known that this is what they're going to look like, now I can look for the R being at my quadrants. So if it's a circle, my R is either going to be here, or it's going to be here, or it's going to be here, or it's going to be here. So I can literally, if it's a circle, plug in my quadrant angles and figure out where my diameter exists. So if I plug in 0 and I get R to be the number on the front here, then I know I found my diameter. If I plug in pi over 2 and it's there, now I know my circle's here. If I plug in pi and it's there, I know my circle's here. If I plug in 3 pi over 2 and I get the R, then I know my circle's at the bottom. So you eliminate a lot of work by just knowing that about a cosine one.
How do you know the R though?
You would plug in, your R is what you get by plugging in. But if when you plug in you get A, then that's your diameter, then that means you've hit the point, that's the furthest point from your pole.
So you have to get the after you plug in, you have to get the A.
You're looking to get the A, correct. And if it's cosine, it's either going to be here or it's going to be here.
Right.
And if it's sine, it's either going to be here or it's going to be here. So you literally only have to plug in 2 things for sines and cosines. The only other thing, and it's not on here, is if it just has a value. So if it just says a number like R equals 3, and there is no sine and there is no cosine, this is a circle with a center at 0, 0 and a radius of 3. So this is literally a circle that starts at 0, 0. You'd go to the right 3, you'd go up 3, left 3, down 3, and you'd make your circle. So anytime you don't have a trig function and it's just R equals, that is a circle. And your radius, it's literally telling you R is 3. That means from the center to the side is 3. So if you know these things, it eliminates so much work from what you have to plug in.
The equation would be
R equals a number, just a number. Yep. All right, then the last one that we didn't touch on yet is called a Lemnis Gate. A Lemnis Gate looks like an infinity symbol. It has 2 petals only. This is the only time R is squared. So these are the easiest to identify in my opinion because it's the only time R is squared. So then it's equal to A squared equals sine or cosine of 2 theta. It will also have a 2 on the theta. Okay, so those 2 things are going to happen. It's going to be R squared and it's going to be 2 theta. Then the number on the front is the A squared. So whatever number is here, let's say it's 16, this means that my A is 4, and that's my loop length. I don't call it a petal because it's not a rose, but it's basically the length of your loop, okay? So the square root of the number that's on the front is going to be the largest loop, so as far out as you go. If it has, so now that the rules of symmetry don't apply the same way because R is squared. Notice that this has a sign in its equation, but it is not symmetric to the pi over 2 line, okay? So the rules of those shortcuts only apply if R is raised to the first power. If it is squared, it's always going to be symmetric. If it's squared, because the test for pole is to replace R with negative R, if it's squared, it's always going to have pole symmetry, which means whatever's happening in the top right is always going to be happening in the top left. So my infinity symbol will either be top right, bottom left, or top left, bottom right. And then this still has symmetry to the pole, even though it also has symmetry to the polar axis and the pi over 2 line, it also still has symmetry to the pole. Because again, it's r squared. So if you plug in a negative r, it's always going to go back to the original. All right, so we did this one yesterday, right? This is the rows we did yesterday? Mm-hmm. Yes. We're going to example 4. So again, same set of instructions. Analyze the graph of r squared equals 9 sine 2 theta. And then your goal is to identify the type of curve, the symmetry, and the zeros means just like you need to plot your points. Verify using a graphing calculator. So because it's r squared, this is what kind of graph? A Lemnis Gate. What kind of symmetry do we know it has? Pole symmetry. Okay. If it was cosine, it would also have polar axis, but it's sine. So now I know I want to pull in my graph. I want to figure out where r is my or where my largest loop is, right? And I get that from the term on the front being square rooted. So if a squared is 9, then a is 3. So the largest point out from here is 3. I can find this 2 ways. One, literally check my quadrant angles, see if it happens at one of those. That would be the most basic way. Or if it's not happening there, then I need to plug in places from my quadrant. So there's a lot of plug and check here. The other way is work backwards. So I would do what we did yesterday, which is say if r squared, so I want my radius to be 3. So 3 squared equals 9 sine 2 theta. Work backwards to get to theta. So if this is 9 equals 9 sine 2 theta, I would divide both sides by 9. 1 equals sine 2 theta. I'm trying to figure out from here where is sine 1, and that happens where?
By sine 1.
So this I look at later. First, I'm looking for where sine is 1, right?
Why 1 though?
Because that's what this says. What it's equal to.
Okay.
So where is sine 1? Pi over 2. So pi over 2 equals 2 theta, and then I would divide both sides by 2, or multiply by a half, and theta is pi over 4. So that tells me that it is 3 at pi over 4. So if I didn't do it this way, if I had plugged in 0, I would have gotten 0. If I plugged in pi over 2, I would have gotten 0. It wouldn't have happened until I plugged over pi over 4 that I would have found that 4 if I'm guessing, if I'm plugging in and guessing and checking.
Couldn't you just say that it was a sine, so like you know it's going diagonal and plug in those?
But it could be the other direction diagonally. You can plug in pi over 4s, yeah. You can plug in pi over 4, 3 pi over 4, 5 pi over, you can do it that way, yeah. All right, so then if this is a Lemnis Gate, where do I think the other loop is happening? And the other side in the third, in the third quadrant where it would be 5 pi over 4. So I'm going to confirm that by doing r squared equals 9 sine 2 theta is 5 pi over 4. R squared equals 9 sine, well, let me simplify this. 2 goes in here twice. 5 pi over 2. Where's 5 pi over 2? Is that on your unit circle? No, it's coterminal angle, right? 5 over 2 would be what? In mixed number form. 2 1/2 pi. Where's that angle? At the top. All the way around to 2, right? And then at the top. So what's the sign there? Not the angle, the sign. 1, good. So then 9 times 1 equals r squared, and r would equal 3. So that just confirms what we had anticipated about the rest of my graph.
So what do you not have to do? Because like you already know.
I would just confirm it, that's all. So you either have to know to plug it back in like this, or you're going to give me a bunch of, you can have that choice. You're going to either have to plug in points to prove that it is where it is, or you use the like quick checks like that.
But you have to do
No.
Oh.
Yeah.
Okay.
You have to give me one or the other. So you'd either be plugging in something like 0, pi over 4, pi over 2, and then once you find the first loop, then you're going to find the second loop.
Like you already know.
Correct. Yep. Okay, now we're going to use the graphing utility to verify. So here's the catch with roses. With Lemnis gates. This is not an R equals. So if I want to plug this in, what do I have to do to this equation first? Square root. I have to do plus and minus the square root. So I would get R equals plus and minus the square root of 9 sine 2 theta. Now you don't have to go through the work of actually square rooting that, but this means you have to enter in two equations. One is going to be a positive square root 9 sine 2 theta, and one is going to be a negative square root 9 sine 2 theta. All right, so again, my calculator has to be in polar and radians, and then I go to the y equals, and it already says R equals instead of y, and then I have to do the square root of 9 sine 2 theta, and then I have to do negative square root 9 sine 2 theta. Then I hit graph, and it's going to give you your Lemnis gate. Questions? So Lemnis gate's the only one you're going to have to do that extra step of the square rooting in order to plug it in the calculator. The rest you can just plug in. But you're going to have to square root it, and you're going to have to remember to do plus and minus. So having said that, obviously you're not going to have a graphing utility on this portion of your test. You need to know how to do these by hand. You can just do these to check. And it's the X button. That's why when you put it in polar, the X becomes theta. Questions? So the first thing I would notice about this is there's parentheses, and you want to get rid of them because that's how you're going to figure out your A and your B. So if I distribute this, it's 2 minus 2 sine theta. And then by looking at this, I know it's a limison because it's got something that's separated by a plus or minus sign. So that's the first part. If it's a limison, then I have to classify it as inner loop, heart-shaped or cardioid, convex, dimpled, okay? So the A is the one that's by itself. The B is what's attached to this. So this would be 2 over 2. I ignored the sign there, and that's 1. So if A over B equals 1, this is a heart-shaped because it goes less than 1, equal to 1, in between 1 and 2, greater than 2, right? So this is the second one in, which is the heart-shaped. So that's going to help me when I go to graph it, know if my points are accurate. The other thing you should know is that because it has sign in it, it's symmetric to what? The y-axis, which we call what? Pi over 2. So it's technically theta equals pi over 2, but I know it's symmetric to this line. So whatever I plug in, first of all, I'm going to choose to plug in from the right side of my graph. I'm going to plug in from quadrant 1 and quadrant 4. You could have picked 2 and 3 and then go back the other way. It doesn't matter. But obviously, I think you're more familiar with quadrants 1 than you are 2 and 3. So I'm going to pick quadrant 1, quadrant 4, and then I'm going to duplicate those points over to the left. So from quadrant 1, and by quadrant 1, I mean also the quadrants at the top and the bottom, the quadrant angles. So I'm going to do pi over 2. I'm going to do pi over 4. I'm going to do 0, 7 pi over 4, and 3 pi over 2. And then I'm going to take the 3 in between, on the right, so pi over 4, 0, and 7 pi over 4, and reflect it over.
And then for the test, we'll have to have, all the coordinates written down.
You'll have to have, what do you mean all the coordinates? Like you're going to have the work for those points. Is that what you mean?
Yeah, but
yeah.
When we flip it over, do we have to have
no.
what those points are?
Nope.
Okay.
Your graphs should show them, that's all. So I'm going to start with pi over 2. So R equals 2 minus 2 sine pi over 2. The sign at pi over 2, because that coordinate point is 0, 1, is 1. And then 2 minus 2 is 0. So R equals 0 when theta is pi over 2. That's my first plotted point. So that should already tell you that your heart dips in at the top of your graph. So then I'm going to go r equals 2 minus sine pi over 4. Minus 2 sine pi over 4. Pi over 4, my coordinate point is root 2 over 2 and root 2 over 2. The sine there is root 2 over 2. These cancel. I get 2 minus root 2. And yesterday we talked about memorizing root 2 to make our lives easier. And we approximate to be 1.4. So 2 minus 1.4 is 0.6. So that's the r when my theta is pi over 4. So it's 0.6. Then I would do 0. So r equals 2 minus 2 sine 0. The coordinate point at 0 is 1, 0, which means sine is 0. And r is 2 there. 2, 0. So now I know that there's where my r is. And then I'm going to plug in 7 pi over 2. So r equals 2 minus 2 sine 7 pi over, did I say 2? 7 pi over 4. Coordinate point there is root 2 over 2 and negative root 2 over 2. So the sign is negative root 2 over 2. These cancel, and I end up with minus a negative, which becomes positive. So 2 plus root 2, 2 plus 1.4, which is 3.4. So that coordinate point is 3.4, 7 pi over 4. So at 7 pi over 4, I'm going to 3.4. And then the last one I'm going to plug in is 3 pi over 2. R equals 2 minus 2 sine 3 pi over 2. Coordinate point there is 0, negative 1. My y is negative 1. 2 plus 2 is 4. 4, comma, 3 pi over 2. And that takes me to the 4. So you will have a lemison, like you're going to have probably 2 graphs on your test. At minimum, 1 lemison, and then the other one is going to be a rotator. Either a circle or a rose or a Lemnis Gate, okay? But when you do a lemison, it has to be classified as a lemison, then which kind of lemison, then the symmetry, and then based on that symmetry, you're either plugging in points from first and second, if it was symmetric to the polar axis, which is a cosine, or you're plugging in, like we just did, points from first and fourth, because it's going to be symmetric to the sine curve, or to the pi over 2. So now I go to my graph, and I'm going to mirror all of the points I just plotted on the right onto the left. So my pi over, my 0 gets reversed over here. This one would go over here to 2. This one is going to come here. This one is going to come over here. And then I connect those points, and I know it's a heart shape, so I know to make the curve dip in the middle. Questions? So we determined that this is what kind of graph? This is a rose. Okay, how many petals does it have? 3 petals. What's the petal length?
4.
Which means nothing should be bigger than 4. No radius should be bigger than 4, right? Okay, and it's got symmetry to what? To the y or the pi over 2. So if I pull in my graph, and I've got a couple of different approaches with your rows, right? One is I know whatever happens on the right-hand side is going to duplicate over on the left, so I can plug in points from the right-hand side. The other is it's really like a search and find your petal. So one way you can find that is set r equal to the petal length, so 4. So I would say 4 equals 4 sine 3 theta. Divide both sides by 4. All right, so we're solving for r. So this would be 1 equals sine of 3 theta, okay? Then we're working backwards. So which angle has the sign that is 1? Pi over 2. So pi over 2 equals 3 theta. We divide both sides by 3, or multiply by a third here, and theta is pi over 6. So this tells me that one of my petals is at pi over 6. So I got that instead of having to plug in check, I can work backwards. So if this has a petal length of 4, it looks like this. If it's symmetric to my y-axis, where else is a petal? 5 pi over 6, so this would be 4. And then where do we think our third petal is going to look if it's symmetric to the y-axis? On the bottom. How could we make sure that this was our third petal or the other one that we just drew? We could plug in 3 pi over 2. So if I did r equals 4 sine 3 times 3 pi over 2, I would get 4 sine 9 pi over 2. 9 pi over 2 is not on my unit circle. So I convert that to a mixed number, which would be 4 and 1/2 pi. 4 is even, which would be on the right-hand side of my circle, and then go 1/2 past it. I'd be at the top, and that coordinate point is 0, 1, so the sign is 1, and that tells me that coordinate point was correct. 4 pi over 3 would be my third petal. If you don't know how to work backwards, and obviously I strongly recommend working backwards because it's going to save you time. If you don't know how to work backwards, then I would have known to plug in coordinate points from this side. If I plugged in 0, I would have gotten 0. If I plugged in pi over 2, I would have gotten 0. And then I would have had to plug in 3 pi over 2. I would have found that first petal at the bottom. But then to get this petal over here, I would have had to plug in points over on the right-hand side. If you plugged in pi over 4, you're not going to get 4. You're not going to get your petal length. It wouldn't be until you guessed and checked with pi over 6 that you got your petal length. So just keep that in mind. Yep.
So you could have, for the third petal, you could have either plugged in pi over 2 or 3 pi over 2 because you would have gotten the same thing.
Well, pi over 2 would have given you 0. Right? 3 pi over 2. Oh, no, it would have given you negative. Yeah, it would have given you the negative angle. Yeah, it would have also given it to you. 4 sine 3 pi over 2. Yep, that would have been negative 1.
So we kind of just guessed to find the third one. And that, like, that
I mean, you're using logic that it has to be symmetric, so you know it has to fall either there. And if it's 2 on the top and 1 on the bottom, it has to be on the bottom. It's not going to be reversed. You're just really checking it. You're just really confirming it. Yeah.
4 equals 4 sine.
Say again?
4 equals 4 sine 3 beta.
What about it?
Why is 4 equals?
That's how I work backwards to find the petal.
But you said it equal to the first number.
4 is the R. So R, right, A is the number on the front, right? This is my A. And the A is equal to R if it's the petal length. So if you, that's where the petal happens, right? R is ever changing, but if you want to find the longest point, which would be the edge of the petal, you make R A.
So always.
To find the, yeah. Yeah. And then same for Lemnis Gate. Like if this was one of my infinity ones, right? It's just that you have to square root that number to get R. So in a Lemnis Gate, it's a squared there. So it would be 2. Then I would make R2. You'd square it again because the equation is R squared. But you'd work backwards the same way. Yeah.
Also, you plug in A, but then you
square it anyways. Yep. Questions? A little bit more comfortable today than yesterday? Okay, good. So we know it's a limit sign because you're adding or subtracting, and then the A is 3, the B is 6, which means this is less than 1. The A over B is less than 1, which means it's an inner loop. What kind of symmetry does it have? Polar axis symmetry, which means like your x-axis, right? Which means I'm going to plug in from the top of my unit circle. So I'm going to plug in 0, pi over 4, pi over 2, 3 pi over 4, pi, and then I'm going to reflect it underneath. So I would get 3 plus 6 cosine. I'm going to start at 0 and work my way around. 3 plus 6 cosine 0. The cosine is 0 is 1. 3 plus 6 is 9. So it's 9, 0. Then I go to the next one. I'm going to plug in pi over 4. So 3 plus 6 cosine pi over 4. 3 plus 6 times root 2 over 2, which becomes 3 plus 3 root 2. Root 2 is 1.4. 3 times 1.4, is 4.2. 3 plus 4.2 is 7.2. So 7.2 pi over 4 is the next one. 3 plus 6 cosine at pi over 2. Cosine at pi over 2 is 0. So this is 3. 3 plus 6 cosine 3 pi over 4. 3 plus 6 times a negative root 2 over 2. So 3 minus 3 times root 2, and we already did 3 times root 2 is 4.2. So 3 minus 4.2 is negative 1.2. So at 3 pi over 4, I'm going the opposite direction, negative 1.2. So instead of going along 3.4, I'm actually going to end up along 7.4. Then I go to my next one, which is pi. 3 plus 6 cosine pi. 3 plus 6 times cosine at pi is negative 1. 3 minus 6 is negative 3. So I have this weird shape. I know it's going to be an inner loop, so I know it's going to have a general weird shape. The inner loop is going to cross through 0, 0. So if I had plugged in like 3 pi over 2, I might get that 0, 0. It's going to happen at some point. It's always going to cross through 0, 0. So you know you have that point. And we know that this shape is going to go past that pi over 2 line and come back in and circle around. So I can duplicate the points I have right now, everything that's above the x-axis. So this one would come down here. This one is going to end up here. And then the pi over 4, this one's going to end up over here. What I don't have is anything in this area yet. If you aren't sure about it being a loop, or if you're not sure what that graph's going to look like, you can always plug in additional points to find it. But if you know this has to loop around and it's going to come back through here and loop around like that, that's enough for me. So you have to know it's got an inner loop. An inner loop is always going to cross through the pole, so I can add that point on there. And then you can reflect. You don't need more points. But if you're unsure, like everything of these, if you're unsure of what you're doing, you're going to end up plugging in additional points. So you could have plugged in anywhere else from the first quadrant or the second quadrant, any over 3 or any over 6. You would have gotten additional points that would have helped you with that loop. But again, you want to make sure that if you know what you're doing, you're eliminating half the work by knowing it's a loop, and loops cross through the pole. Okay.